All right, we're going to take a look at some ways we can apply similarity to triangles now that we know what it is and how to use scale factor and so forth. So the first topic, which will be the part one of this video, there will be a part two talking about after the first and second page. We've got similarity in right triangles, and then page 3 and page 4 are about two other topics. So we'll split the video in half. So how do we set up the scenario where we have similarity? Well, the altitude of a triangle is the perpendicular line or segment, call it a perpendicular, drawn from the vertex of the triangle to its opposite side. And a triangle has 3 of these. We're only going to draw one, and the one that we're going to draw is going to be from the largest angle to the largest side. So here you can see from a vertex, it goes perpendicular to the other side. That's an altitude. And there are 3 of them. You could draw one here, and you could draw one here as well. But for our theorem, we're interested in the altitude being drawn from the right angle, this right angle here, and then down to the hypotenuse. Okay, so how does the statement go? It's if you have this picture here where you have the altitude CD of a right triangle, you actually end up having 3 similar right triangles. And we have a big one, which is the entire thing. It's been kind of flipped around. We have the smallest one, which we'll call 1. And we have the medium one, which we'll call 2. So it's important to kind of keep these straight. So let's first start with a proof, and then we'll be able to label the triangles. So what you do is you drop down the altitude, which should be perpendicular to the hypotenuse here. And to prove that these are similar, I'm going to go ahead and draw a rectangle here so that this triangle is the same as this triangle, right? And this triangle would be the same as this triangle. I believe you could make some sort of argument, maybe like an angle side angle argument, that those are the same, but they share a hypotenuse and the legs are the same. So maybe even just a side argument. So those are the same. So what we're trying to show is that this upside down right triangle here is similar to both this one and this one at the same time. How do we do that? Well, let's look at the angles. So the big upside down right triangle, which I'll highlight in yellow, we can look at its angles. So I don't know what they are, but I do know that there's going to be one here and there's going to be one here. Let's just say, for the sake of argument, that this is 50 and this is 40. I know it has to have that constraint. It has to be 90 because the entire yellow triangle has to add up to 180 degrees on the inside. But by the way we've drawn this rectangle, we have parallel lines here. So we actually have some, if you look closely on this diagram, we have some alternate interior angles. In other words, this angle right here is a shaded angle. And the same thing would be true over here, right? Because this is the transversal cutting across these parallel lines. Those are alternate interiors. Okay? But if that's the case, these are right angles too, since it's a rectangle. And I think we've got somewhere, because triangle 1 is similar to the big triangle by angle similarity. Because look, the big triangle has the right angle and the black, and triangle 1 also has the right angle and the black. So they're similar. And 2 is similar to the big triangle also by a similarity, because they both have the right angle and the white angle, right and white right there. So because the big one is similar to both 1 and 2, so that means 1 and 2 are similar too. Basically, all of them are now similar, and we can fill in the rest of the angles in here too. So this would be a shaded one, this would be an open one, you see? So that way, if we break this down, every single triangle has a black shaded angle, which we could say is like 50 degrees, and then maybe this one here is 40 degrees, or something like that. Now, you can also label the vertices. So C is this right angle, and D is the right angle for the others. So on the picture, this is the shaded one. So this is A, and this is B. This one's actually right side up in the picture. And this one here has these labels. So, and then these triangles are going to have lengths, and we're going to try and figure out how we can set up these triangles and use similarity to help us find missing lengths. But first of all, let's again kind of back up and make sure that we can decompose. So this triangle, so I always look at these two angles. I like to do the bigger one with the shaded and the not so big one with the open one. And because these are similar, this triangle also needs a shaded one, and this one needs an open one. And that should help a lot with labeling. So I always put the shaded part up top. So for the very big triangle, the big angle's H, and this is G, this has to be F. And then this triangle, which I'll call the second biggest, or the second smallest, if we highlight that, we can see it's G, F, and N. And for the smallest one, the number one smallest, oops, sorry, hold on. I messed that up. I meant to be drawing on. This is this is number 2, right? So let's backtrack there. Okay, here's number 2. Its black angle is G, white angle's F, and this is N. And then if we go down to the smallest one here, this is the big one. The black angle's H, the white angle is G, and this is still N. Okay? So they're twisting and turning. They're literally like flipping, rotating, translating, doing everything. So it can be kind of difficult to keep them straight, but just remember that every triangle is going to have a right angle, a black angle, and a white angle. Let's actually then solve for some x and y. So we still have to break down the picture. So this looks a little bigger than this one. And then I can fill in these here, and they're like that. Black, white, black, white, black, white. Okay. So you can label the vertices if you want, and I will. We'll do A, B, C there. That's the biggest triangle. The second smallest one is this one, right? And that one's actually oriented the right way. So C, D, B. And this little guy here is tilted a little bit, but it has A, D, and C as its vertices, okay? And now we're gonna go back in and label any sides that we know. So what's the length of AB? It looks like it's 13, these together. What's the length of AC? We don't know. There's nothing labeled for AC. And for BC, there's a Y labeled. So I'll put a Y there. For triangle number 1, the smallest one, between the right angle and the black angle is 4. Between D and C is X, and we don't know AC. And then for the middle triangle, triangle 2, between C and D is X, between D and B is 9, and the hypotenuse is Y. All right, so my advice is to look to see if you can make a foursome with any of the sides and hope that it just has one variable. So what I'm looking at right now are these and these, because I can set up a proportion. It'll just be with x, and I think I'll have everything I need to solve it. So what you do is you would say, all right, x, I would do this over this is equal to 9 over x. Why? Because they're similar triangles and they are in proportion, the sides. So I'm going to cross multiply and get x is 6. So I'm going to go ahead and go to where there's x's, and I'm going to write that these are equal to 6. And a huge tool with right triangles and sides is the Pythagorean theorem. So if I ever have a triangle that has all of its sides, except for one, that's a big indicator to me. This one's nice, but I have no idea what the hypotenuse is. Whereas triangle 2 has a 6, a 9, and a y. So from this, I can set up 6 squared plus 9 squared equals y squared. And that's huge. Because then we can just move along, get 117. So the square root of 117 is y, which you could write as 3 square root 13, but who's counting? There we go. So that's kind of how these problems work. This one has you solve for 2 variables. But I'm really concerned that we're just able to break apart the picture into 3 similar triangles. So we'll get another chance to do it here. So this is a very, let's do blue, very big angle right here and a little angle here. Again, I'm looking at this biggest one. So this should be my black and white. And then we know these are similar, so we know that all the triangles have a black and a white angle, so we have to situate that. All of them can be drawn like this with those same angles because they're similar. And then we can go in and label them. So I believe this is just SUT. The smallest one has E at its right angle, and then T is the black or the dark angle, and this is S. And that was 1. And 2 has, between the black and the white is 17. The right angle and the dark angle is 8. And this is X. I guess I went ahead and labeled those. This is going to be S, E, and U, right? Okay, what else can I label? What's the length of TS? That could be useful. Does not tell us. What about SU? SU is 17. And TU is X plus Y, which means we're probably not going to end up using that. And 1 has a Y here, an 8 here, and we don't know TS. All right, so what could we do? I always look for Pythagorean theorem first. So do any of the triangles have 2 sides as numbers plus a variable we want? And yes, that is very true. We can use this one. So it's going to be 8 squared plus x squared is 17 squared. And if we do a little bit of work and subtract 64 from both sides, we actually get an even 15. So this x is equal to 15, which completely solves that triangle, which is huge because then we can probably compare this as a reference point to another similar triangle. And yeah, we know this is now y plus 15, but again, probably not going to use that. Now we're going to look to maybe set up a ratio. So how about this short leg with this long leg? So you could set that up as 8 over y is 15 over 8. So cross multiply, and y ends up being that fraction, which is around 4.3. So This is kind of the hairy part with it, trying to figure out how to set up the proportion. But it's really just focusing one at a. You have to really search sometimes, but just searching to see if is a foursome that you could that only has one variable that you could set up a proportion with. So if you'd like more practice, come talk to me. Let me know. I can come up with more problems. But you can try these two homeworks to start. All right, and then the part